Sure. Let's dive into the concept of derivatives in calculus. What is a derivative? A derivative represents the rate at which a function is changing at any given point. In simpler terms, it gives us the slope of the tangent line to the function's graph at a specific point. This can be thought of as the function's instantaneous rate of change. Formal definition. The derivative of a function f(x) at a point x is defined as: this limit, if it exists, gives the slope of the tangent line to the graph of f(x) at the point x. Basic rules of differentiation. Constant rule, the derivative of a constant is 0. Constant rule, the derivative of a constant is 0. Power rule, if f(x) equals x to the power of n, then f(x) equals nx caret n1. Power rule, if f(x) equals x to the power of n, then f(x) equals nx caret n1. Sum rule, the derivative of a sum of functions is the sum of their derivatives. Sum rule, the derivative of a sum of functions is the sum of their derivatives. Product rule, if f(x) and gx are functions, then. Quotient rule, if f(x) and gx are functions, then. Chain rule, if a function y depends on u, which in turn depends on x, then. Examples. Derivative of f(x) equals x squared. Derivative of f(x) equals \sin x. Derivative of f(x) equals e to the power of x. Applications. Physics. Derivatives are used to find velocity and acceleration from position functions. Economics. They help in finding marginal cost and revenue. Biology. Used in modeling population growth rates. Would you like to see more examples or dive into a specific application? Absolutely. Let's explore exponential functions. What is an exponential function? An exponential function is a mathematical function of the form where a is a constant and represents the initial value when x equals 0. B is the base of the exponential function and is a positive real number. X is the exponent and can be any real number. Key characteristics. Growth and decay. If b greater than 1, the function represents exponential growth. If 0 less than 1, the function represents exponential decay. Horizontal asymptote. The graph of an exponential function has a horizontal asymptote, typically the x-axis, y equals 0, which the function approaches but never touches. Domain and range. The domain of an exponential function is all real numbers, --inft ax u \inft. The range is all positive real numbers, 0 ef x u \inft, if a is 0. Examples. Exponential growth. Here a equals 2 and b equals 3. As x increases, fx grows rapidly. Exponential decay. Here a equals 5 and b equals 0.5. As x increases, fx decreases rapidly. Applications. Population growth. Exponential functions model population growth where the rate of growth is proportional to the current population. Radioactive decay. The decay of radioactive substances is modeled by exponential decay functions. Finance. Compound interest calculations use exponential functions to determine the growth of investments over time. Graphing exponential functions. To graph an exponential function, follow these steps. Identify the initial value a and the base b. Plot the point 0a since f0 equals a. Determine a few more points by choosing values for x and calculating fx. Draw a smooth curve through the points, noting the horizontal asymptote. Example graph. Let's graph fx equals 2 \3 to the power of x. When x equals 0, f0 equals 2 \3 to the power of 0 equals 2. When x equals 1, f1 equals 2 \3 to the power of 1 equals 6. When x equals -1, f minus 1 equals 2 backslash dot 3 caret minus 1 equals backslash frac 2 3. Plot these points and draw a smooth curve through them, noting that the curve approaches the x-axis as x becomes more negative. Would you like to see more examples or dive into a specific application of exponential functions?